So students, let us continue our discussion on the finite sets in finite sets. So in the previous lecture, that is lecture 6, we had discussed about the definition of finite set in terms of bijection from the first n natural numbers to S. So you observe that S is finite if it is either empty or there exists a bijection from n, that is the set of first n natural numbers to S for some n. Okay, this was the definition. Now let S be finite and T be another set such that there exists a bijection from T to S. Then also we can conclude that T is a finite set because the composition of two bijections is a bijection. So there is a bijection from T to S and S is already given to be finite. That means there is a bijection from S to the first set of first n natural numbers. Then T from there is also a bijection from T to the first set of first n natural numbers, right? So if we are given a finite set and if we can find a bijection from another set to that particular finite set, then the new set that we are talking about is also a finite set. So it is not necessary to construct bijection from the set to the first n natural numbers only. If we already know that a given set is finite and we want to show another set is finite, we may also try constructing a bijection from that set to the given finite set. Okay, so these are the same. Okay, so yeah, so let us do this theorem. So in the last lecture, the last result that I told you, there was some not error, basically there was some lack of clarity in the presentation of the proof. So we will do that proof again today using this particular result. So let us do this result first. Let S and T be sets and T be a subset of S. Okay, so it's quite obvious, if S is a finite set, then its subsets will be finite. Okay, so but then we have to prove it rigorously from the definition that we have adopted. We have to prove it rigorously from there. So every subset of a finite set is finite. This is the first result. If S is finite, then T is also finite. And the contrapositive of this is if T is infinite, that is if the subset is infinite, then the superset will be infinite. Okay, so every superset of a infinite set is infinite, right? So the second one is just the contrapositive of the first. So if we just prove the first one, the second one will follow, right? So let us start this. If the subset is phi, that is empty, then T is finite by definition. So let T not equal to phi. So we proceed by the induction on the number of elements of S. Okay, so suppose S has one elements. If the set has S has one element, then the only possible non-empty subset of S is S itself, that is T is exactly equal to S, and so T is finite because S is finite. Okay, S is a set having one element, so it's finite. So the result is true for n equal to 1, that is every non-empty subset of a finite set having one element is finite. Okay, so we can suppose that the result is true for any non-empty set with k elements. That is our induction hypothesis is every non-empty subset of a set with k elements is finite. Okay, so we will show that every non-empty subset of a set with k plus 1 elements is finite. Okay, then by induction our result will follow. So let S be a set with k plus 1 elements. Then by definition there exists a bijection from n k plus 1 to S, that is the set of first k plus 1 natural numbers to S. So there are two possibilities for the k plus 1th element. Fk plus 1 may belong to the subset T, or Fk plus 1 doesn't belong to the subset T. Okay, these are the two possibilities, right? So if Fk plus 1 is not in T, then T is a subset of S minus Fk plus 1, right? Fk plus 1 is not inside the subset T, okay, but it is inside the set S. So from the set S, if I remove the element Fk plus 1, then that particular set will be a superset of T. Okay, because T does not contain this element. So even if we remove that particular element, T still remains a subset of the set S minus Fk plus 1. Okay, but what is this this set S minus Fk plus 1? This set has k elements because S has k plus 1 elements. We are removing one element from S, and in the last lecture also we had done one theorem. If we remove a single element from a given set, then the number of elements decreases by 1. That rigorously we had proved by actually constructing a bijection. Okay, so this has got k elements, and by induction hypothesis every subset of a set having k elements is finite. So t is finite. Okay, so if k plus 1 doesn't belong to t, it follows that t is finite. Next case is if f of k plus 1 belongs to t. Then what happens if we remove f of k plus 1 from t? This will also be a subset of S minus f of k plus 1. Right. So removal of f of k plus 1 from t as well as fk plus 1 doesn't make any difference because fk plus 1 is an element inside t. So you remove f of k plus 1, it is still a subset of S minus f of k plus 1. Okay. So, but S minus f of k plus 1 again has k elements, and so by induction hypothesis t minus f of k plus 1 is finite. And in the last lecture we had also done another theorem that if A and B are two finite sets which were disjoint, then their union is also finite. So t minus fk plus 1 union with fk plus 1 is finite, but what is this union? Their union is nothing but t, so t is finite. So we have proved that if every subset of a set with k elements is finite, then every subset of a set with k plus 1 elements is also finite. That means the result is true for every natural number, that is every subset of a set with any n elements, where n is any natural number, is also finite. Okay. So thus by principle of mathematical induction, every subset of a finite set is finite. And the second result is just the contrapositive. So S is finite implies every subset of S is finite. The contrapositive is if there is a subset which is infinite, then the original set or the superset will also be infinite. Okay. The last part of theorem 1, let us try this again that I had mentioned. So we can prove it easily using the earlier theorem. So if C is an infinite set and B is a finite set, then C minus B is infinite. Okay. So if we remove a finite set from an infinite set, then also the remaining set remains infinite. Okay, that is what. So removal of finitely many elements from an infinite set doesn't matter. Okay, the set remains as infinite. So given B is a finite set and C is infinite, suppose that C minus B is finite. Okay, then B union C minus B, which is same as B union C, is finite by the result that we had proved, the union of two finite sets. So now, what is C? C is a subset of B union C, and we have just shown that every subset of a finite set is finite. That means C is finite, but this contradicts the fact that C is infinite. So C minus B, our assumption was incorrect. So C minus B has to be finite, has to be infinite. Okay. So this was about finite sets. Now we generalize this notion to larger sets. So we introduce the definition of countable set. So before I introduce this definition, I would like all of you to see this animation. Which set has got more elements? Are there more natural numbers or more even numbers? What do you think? Are there more natural numbers than even numbers? Right. So it may appear that there are more natural numbers because you see the set of even numbers, it contains only 2, 4, 6, 8. So the elements 1, 3, 5, 7, all the odd numbers are missing. So at first it may appear that there are in fact more natural numbers than even numbers. But once you see this illustration, you will come to know that this is not the case. There is something to think about. So these are the, say, let us consider these natural numbers 1, 2, 3, 4, 5. They are natural numbers, and the list goes on. And the even numbers, let's say 2, 4, 6, 8, 10. Okay, these are the even numbers, and the list goes on. Okay, so at first glance it may appear that no, the first set will have more elements, because the first set is having 1 here, but the second set is not having 1, right? The first set is having 3, but the second set is not having 3. But the first set is having 5, but the second set doesn't have 5. Okay, whereas every element of the second set is there in the first set. So it may appear that the natural numbers are more in number than even numbers. Okay, but if we try to think a little bit about the even numbers, this 2 can be written as 2 into 1, right? 4 can be written as 2 into 2. Okay, 6 can be written as 2 into 3, right? 8 can be written as 2 into 4, and 5 can be written as 10 can be written as 2 into 5. Okay, so now if you compare the even numbers with the natural number, you see for the first natural number there is a corresponding even number 2 into 1. For the second natural number there is a corresponding even number, that is 2 into 2, right? So we have something like this: 1 corresponds to 2 into 1, right? 2 corresponds to 2 into 2, 3 corresponds to 2 into 3, 4 corresponds to 4 into 4, 2 into 4, and 5 corresponds to 2 into 5, right? So ultimately we see that we can associate every natural number to a even number. Similarly, we can associate every natural number, every even number to a natural number, and the association can be done in a unique way. That is, 1 is assigned to 2 into 1, 2 is assigned to 2 into 2. So 2 different natural numbers are not assigned to the same even number. Okay, so actually what we are talking of is we have actually constructed a bijection from the set of natural numbers to the set of even numbers, and because of this bijection we can say that there are as many even numbers as there are natural numbers. The set of even numbers is not a small set. Okay, there are as many natural numbers as there are even numbers, as there are as many even numbers as there are natural numbers. Okay, so this is what we will study in the countable uncountable sets. Okay, so let us go back to this, the definition. So if we have a countable set, so a set S is said to be countable if it is either finite or if there exists a bijection from the set of natural numbers to S, or equivalently the other way, from S to N. Okay, because inverse of a bijection is bijection, right? So a set is said to be countable if it is either finite or if there exists a bijection between N and S. If we can construct a bijection between N and S, then we can say that it's a countable set. Okay, so the natural numbers, they are used for counting, and that is why they are kept as the standard here. Okay, so a set is uncountable if it is not countable. That means if we cannot find any bijection from N to S, then the set will be uncountable. Okay, so a countable set that is not finite is also referred to as a countably infinite set. Okay, so the set of natural numbers itself is a countably infinite set. So by properties of bijections, a set is countable if and only if there exists a bijection from T. A set T is countable if and only if there exists a bijection from T to another countable set. So this is just similar to the remark that I made for finite set. So it is not always necessary to construct actual bijection from N to S. So in many examples you may see that we already have a standard countable set, and suppose I want to show another set is countable, then we try to construct a bijection from that set to this standard countable set. So this also follows from the properties of bijection. Okay, composition of two bijection is bijection. Okay, so these are equivalent things. So by definition, the set of natural numbers N is countable. Okay, because the identity map I from n to n defined by ix equal to x for all x, it is always a bijection, right? So the set of natural numbers itself is a countable set, and it is actually countably infinite set because there are infinitely many natural numbers. So so first result, let us try, show that the set of even natural numbers is countable. So the illustration that I showed you, so let A be the set of even natural numbers. So we consider the map f from n to e, the set of natural numbers to the set of even numbers defined by the natural way that we had already shown. F of n is equal to 2 into n for every natural number, right? So then f is a bijection as shown below. How f is a bijection? F is 1 1. Okay, this is just a routine exercise that you have been doing since your higher secondary days. So I want to show that the function twice n is a 1 1 function. So that means we start with any elements n and m in the set of natural numbers such that their images are equal. Then we show that the elements are themselves equal. So fn equal to fm. So fn is twice n, and fm is twice m. So n equal to m. F is onto, if we take any y inside the even number, then y is even. So y can be written as, so any even number can be written as 2 into some number. Even number means numbers which are divisible by 2. So this follows from the divisibility property of integers. So y can be written as 2 into n for some natural number. So y is ultimately f of n, right? That means every element in E has a pre-image. Okay. We may also argue that this way, if since y is even, so 2 divides y. So y by 2 is a natural number, right? 2 divides y. So y by 2 is a natural number. So let n equal to y by 2. Then f of n is f of y by 2, which is 2 into y by 2, that is y. Okay, so we have constructed an element from y which is acting as a pre-image of y. Okay, so thus f is a bijection. Hence the set of even natural numbers is countable. Okay, similar to this, we can also show that the set of odd natural numbers is countable. That is countably infinite actually, because there is a bijection between n and set of odd natural numbers. So let O be the set of odd natural numbers. So what will be the bijection now? It's very simple. F of n equal to twice n minus 1, that is bijection. Okay. So then f is 1 1. So let n comma m belongs to natural numbers with fn equal to fm. Then fn is twice n minus 1, fm is twice m minus 1. So from that it will follow that n is equal to m. Okay, so f is 1 1. F is on 2, let y be any odd number. Then y is odd, so y plus 1 is even, right? So 2 divides y plus 1. So there exists a natural number n such that y plus 1 can be written as 2 into n, right? So from there you can see what is y. Y is actually twice n minus 1, and twice n minus 1 is nothing but f of n. Okay. So thus f is a bijection, and so the set of odd natural numbers is countable. Okay. So this was about natural and odd. So till now we have done with subsets. Please observe that we have just shown that there are as many natural numbers, odd numbers as there are natural numbers. But now we will also do it with superset. Okay, so show that the set of integers is countable. Okay, so we cannot say that there are more integers than the set of natural numbers. Okay, actually there are as many integers as there are natural numbers. Okay, so we need to construct a bijection from n to z. So let z be the set of integers. We construct the function. So what we do is we take all even numbers to positive integers. We take all odd numbers to negative or say non-positive integers. Okay, including 0. So this is what we do. F of n is n by 2 if n is even, and f of n is minus of n minus 1 by 2 if n is odd. Okay, so what we are doing is f of what will be f of 1? F of 1 will be 0, right? F of 2 will be 2 by 2, that is 1. F of 3 will be, since 3 is odd, it is minus of 3 minus 1 by 2, that is minus 1. Okay, f of 4 will be 2. Then f of 5 will be minus 2. Okay, so this way we are counting 3, then minus 3. Okay, so this way the counting goes on. Okay, so this is exactly what we are doing using this function. Okay, we could have done it the other way. F of n equal to minus n by 2 if n is even, and n minus 1 by 2 if n is odd. Okay, that way also it's possible. So please note that the bijections may not be unique. In fact, there are infinitely many bijections between n and z. Okay, once we construct one bijection, just interchange two elements, then you get a different bijection. Okay, so once you have a bijection between a set n to z or n to any set, there are infinitely many bijections. Okay, so the bijection that I construct may not be the same as the bijection that you construct, but the thing is that it should be actually a bijection. Okay, so the construction should be correct. Okay, that is what. So let us prove that f is 1 1. So we start with n and m inside the set of natural numbers with fn equal to fm. So there are several cases, n and m may be both even. Okay, so if they are both even, then the values of the functions are n by 2 and m by 2. So they are equal. So this implies that n is equal to m. If n and m are both odd, in that case fn equal to fm will imply that minus n minus 1 by 2 equal to minus m minus 1 by 2. So and this will imply that n equal to m. And if n is odd and m is even, okay, the other case, then what will happen? Fn is less than or equal to 0 and fm will be greater than or equal to 1. So fn and fm can never be equal. Okay, so if n is odd, m is even, then equality is not possible. If the other way, if n is even, m is odd, then also the equality doesn't hold. So n not equal to m implies fn not equal to fm. Okay, so in all possible cases we have actually proved this. Fn equal to fm implies n equal to m. Hence f is 1 1. Now f is on to how to show it. Let y belongs to z be any integer. Then if y is greater than or equal to 1, then twice y is an even natural number. Okay, so n equal to twice y. If you take n equal to twice y, then f of n will be n by 2, that is y. Okay, and if y is negative or equal to 0, so y less than or equal to 0, then minus y is greater than or equal to 0, and minus twice y is also greater than or equal to 0. So if you add on 1 on both sides, then 1 minus twice y is greater than or equal to 1. So our aim is actually to construct a natural number from the given integer. Okay, so here it's natural numbers are positive, so our plan is to make it positive. Okay, so yeah, so actually it follows from the substitution, n minus of n minus 1 by 2 equal to 2 equal to y. So this will mean that n equal to 1 minus twice y. So from there you can get the hint how to construct this. Okay, so and let n equal to 1 minus twice y, then n is odd, and by definition f of n will be minus of n minus 1 by 2, and that will give you f of n is y. So f is onto, hence f is a bijection and z is a countable set. Okay, so the set of integers is also countable, and there are as many integers as there are natural numbers. Okay, we cannot say that there are more integers. Okay, so there are several other interesting results on this. We will in fact show that the set of rational numbers is also countable. There are as many rational numbers as there are integers, or as there are natural numbers. Okay, so we cannot say that there are more rational numbers. The set of rational numbers itself is countable set. Okay, so we will do that in the next video. So till then, please try to go through the proof and try to do those proofs yourselves. Okay, only then you can understand. Thanks.